So, hello everybody, and welcome to Intro to Computer Vision, Python's OpenCV library. I am Chase Bastion, a co-technical chair along with
Tim, another one.
All right, we got your mom joining in today. So
really named your mom?
Yep.
Welcome. Oh, wow. Okay. Anyways, so yeah, installation NumPy should be included with Python. If you guys have Python, and we're going to be working with the OpenCV library, which is easily installed. As long as you have Python 3, pip should be included. It's like a Python library manager. So you just pull out any terminal and you write pip3 install OpenCV Python, and we can just wait a bit while you guys are doing that.
Yeah.
And if NumPy is not installed, you can also just pip3 install NumPy.
Shoutouts to pip. So while we wait for everybody, if you don't have Python and everything installed, go ahead and get that going. We're going to talk a little bit about the history of Open Computer Vision.
Some background information. OpenCV stands for it's open source computer vision library, hence the name. And it was first released in 2000, and it was actually part of a IEEE conference on, conference on computer vision and image processing. So, kind of a name drop. We're part of that. There's support for C++, Python, Java, and even support for MATLAB if you so wish to work like that, which sucks. And the Python OpenCV library contains 2,500 plus algorithms that you can use in a large collection of functions for all sorts of image processing and related computer vision work. Yeah. And then continuing on, the NumPy library should be a built-in Python library. It's useful for array manipulation as well as other high-end math, such as you can use it for linear algebra, you'll use it for differentials, any sorts of calculus. And it's high level, but simple to use with easy, simple syntax, especially with Python syntax, which is even easier than normal.
Yeah.
And it's got applications in data science and machine learning. So those are like the depths that you're interested in. NumPy is a library that you should become very familiar with and you will be using often.
And just to give you a little more time on these downloads and everything, we're going to go. So today's workshop it's some intro to OpenCV and some of the functions and functionality you can get with the library. Specifically, our end goal today is we're going to be trying and build a motion tracking system. So any motion in a video to just kind of draw outlines around whatever's moving and kind of track it as it goes along. And so to do that, we're going to be doing a couple different techniques that are quite consistent to pretty much any computer vision you'll be working with. So in the case of motion specifically, we're going to be doing some built-in functions called differencing in OpenCV. And that is because, motion in video is just like the difference between like stop motion or whatever, where you draw on like little note things and flip through it and things move. So that kind of concept, so we'll be using differencing for that. And then something you'll find yourself, if you continue into computer vision at all, doing a lot is kind of cleaning up whatever you're looking at in the image. So oftentimes you'll turn it into black and white and do some filtering and thresholding to get rid of things and get only stuff of interest. And then perhaps one of the biggest and like most useful things that the OpenCV library offers is its ability to draw contours, which are just outlines of shapes or things of interest that you have selected in your image. And yeah, that function, no clue how it works. It's just a bunch of math, but the fact that it does draw outlines for us is super cool and super useful. So that's just a little bit of oversight in what we're going to be doing today. Hopefully that gave everybody ample enough time to get Python and OpenCV and NumPy going so that you can follow along if you so choose. So the slides and the recording of this will be made available at the end. So if you're not able to follow along as we pace along, you can also try everything we're going to be doing on your own. And there should be a little bit of time after the workshop where me and Tim will just be around to answer questions as well if you end up getting stuck along the way.
Oh, and one quick note, we are recording. We have to make that public known to you guys. So,
I think these days, I think Zoom added a feature where if you're in a room that is like recorded by default, it tells you.
So,
So
you know, if you're not comfortable with
yeah.
recording, you don't have to be here and you can watch the recording. But anyways, so if you guys should have OpenCV installed by now, and one way to test is if you just write open or import CV2 in your Python document. I'm going to be using VS Code, but feel free to use whatever you want. And we also check import NumPy as NP. So if you go ahead and run this, write Python 3, and then write test.py. If there's no errors, then it should be installed. And yeah, if you have any questions, let us know if it's working for you guys or not.
Make the text much bigger.
For this?
Yes, I think.
Okay, can I do that actually? Oh, you can. Okay.
Awesome.
Is that good, or should I make it bigger? We can do one bigger, I think.
If it means anything, I can see it on my very small tablet screen with all my split host views. So hopefully everybody else. You said a little bit bigger.
A little bit bigger.
Beautiful.
Nice.
That's
okay.
So large.
That's
all right. We got a TY. That means we're good.
Okay. I think that's good. That's fine. All right. Anyways, so first thing we'll talk about is images. This is just a general like topic in all of computer science and just computers. Images, how they're stored is just pixel values. So most images are 3D array of, you'll have R, G, and B, red, green, blue. However, in OpenCV, an image is backwards, just because I think when OpenCV was first being created, that was just the popular style. So in OpenCV, it's BGR. And we can see this by, let's say, I open up any image. So let's just say frame 1 for now. CV2.imread. This is how you open up any image, by the way, with the CV library. Just write imread, and then you will put the name of the image you want to open. Like, for example, this one's called frame1.jpg. We'll open this. And your images have to be in the same directory as your main Python file, or the other option is to write out the full, the full address. And I think if you're on Windows, you have to write the full directory regardless, like the whole like d/::, whatever it is, the long thing. So if we were to, so that's how we open it. If I were to write print frame1 and we run this, you can see that, the image is nothing more than 3 sets of arrays, and these are all the values of that image in pixels. Moving on, we have grayscale images, which are same concept, except it's only one-dimensional and goes from 0 to 255, just like R, G, and B. So we were to convert this. Let's call this gray one. So go to CV2 color. We'll take our original image that we're converting. We have a built-in keyword CV2.color. This is a constant, and we'll do BGR, which it's currently in, we'll do gray, so it's in grayscale. So now, if we were to print the same image and we run it again, now it's just, instead of a 3D array of 3 different layers, it's just 1 layer now of colors from 0 to 255 in grayscale. And moving on, first topic.
So the first thing we're going to need to do to build our motion tracking is to actually track that motion. So like I was talking about with like that flip note drawing or whatever, the way to track motion between 2 different frames, aka motion in a video, is going to be to find the difference between those 2 frames. So I have a great example on this slide. I'm really proud of this one. This is actually a Where's Waldo picture. And then I don't remember which one's which because I can't tell them apart. But one of them is Where's Waldo with Waldo removed. And as you might be able to barely see in that middle black image, that's actually the difference of the 2 frames that you get when you put this in OpenCV. And it looks like there's actually like 2 white dots. I don't know why. There should only be 1 removed Waldo. But how you get that in OpenCV is the function called absdiff. And so that takes in 2 images. Oh, thank you. Whoa, do the annotations for professional here.
I think it's this
and so this absdiff function in OpenCV, it takes in those 2 images, and then it just basically subtracts them 2. And it returns a grayscale image with the absolute difference between the 2 frames. So if there's a huge difference between 1 pixel in one picture and then the other pixel in the second, that pixel will have a larger, more white value. And so those white values are going to be what we're working. That's actually going to be the motion, essentially, in our videos.
So let's say, oh, I got to clear this. Clear cloud drawings. Should be good. Oh, close that. Okay, so let's open up another image. We have a second frame. I read frame2.jpg. These frames should both be included in the zip file that we linked at the beginning of the workshop, but you can always feel free to use your own content, anything you have. So now we wanted to print these images and show them. We do im.show, and we'll name this one frame1. It's just a name at the top, and this will be frame1, cv2.imshow, frame2, frame2. And if I were to run this, this would not last very long. It drops instantly. So we got to keep a way to keep it on the screen. So we had a wait key in Python, or in the CV library. cv2.wait key. And you put a time in it of any sort of delay, however long you want the picture to stay up. In this case, we'll do 0, which is unlimited. It'll stay forever. And afterwards, we want it to cv2 want to destroy all current windows open. So now if we check this out. Oh, okay, so it's really big. So that's an issue. So if we want, we can scale this out. And how we're going to scale it is we will, let me know if I'm going too fast, by the way. So we'll define a scale. We'll have our width equal to the integer. Oh, actually, we'll just do frame1.shape. So as we previously discussed, I got that shape. The images are kept in arrays, so they all have a size. So we just do shape1. This is the horizontal. It's like how long the array is. That's the width. And we'll scale it down by 25%. And then height, same concept. And the shape, we'll do the height and then scale it by 25%. And we want everything to be whole numbers, so we'll just turn it into an integer for now. And once we do that, we can define our scale as a tuple, width and height. So we have that so far. Should be good. And once we get to that point, let's just comment this out for now. We don't need that. Once we have our scale, we can scale our images. So we'll have our frame1. We'll use the resize function that comes with the CV2 library. And what does the resize is the original image we want to our new scale, which is that same concept for the second image. cv2.resize frame2, and then apply it to the same scale. So after we resize the photos, we run our code again. This is a much more manageable size. We can actually see everything that's going on. And we look at them. The human eye, we can't tell that much difference between these two photos. They probably look exactly the same because they're consecutive frames in a video. So we can't tell what's going on, but we can use math to figure out what's going on. So we're going to convert both images to grayscale. So we have a first one. Let's just repeat the same process. Convert color, frame2, cv2 dot color gr to gray. And then now we can use the absolute differencing function that we previously established how it works. So we'll create a new image. We'll call this one the overlap image, and it'll be equal to cv2.absolute difference. Oh, and by the way, if you guys are using VS Code also and you see a bunch of red squiggles, that's just because the PyLinter that we're using doesn't recognize this as like a built-in function, and you can just ignore it, but it should be fine. So yeah, it has no member. Anyways, so we can use our absolute diff function. So what was the first thing? We have our first image and our second image. And now let's print this overlap and see what it looks like. IMShow overlap. Now we run it. Okay, so previously our frames looked pretty much identical. We can't tell the difference, but when we run it through an overlap function and see where the pixel value is different, we can see now. So for the most part, let's say the green part, they're exactly the same on both ends. So the difference is 0, which is why it's just black. And any part where the car's moved, now we can see, we're starting to get an image of where our car is and where it's moved between frames. The issue, however, is if you notice, we also have all these extra little squiggles. That's from the camera shaking a bit. And so this is just extra noise of the pathway. We don't really want to care about this. So what we want to do is we want to get rid of this. And Chase can explain how we're going to do that.
So this is a super common technique you'll see in any like OpenCV and computer vision focused thing, is that you oftentimes have a lot of noise and stuff that you don't really care that's changing between frames, or honestly you just don't want in the frame because you're focusing on specific objects. And so one of the ways to get rid of those is, first of all, you're likely going to want to do most of your computer vision manipulations in black and white because it's usually easier to see if you don't have to worry about colors or anything. So that's why our image, and especially the difference one, ended up in black and white. And now that we have that black and white image, if we want to get rid of those squiggles Tim was talking about, you'll notice that the squiggles themselves, it's such a small difference between the two frames that the actual value of those squiggles compared to the actual movement we're trying to track is smaller. And so if we wanted to filter out those smaller pixel values, if they're under a certain threshold, we use the OpenCV function, cv2.threshold. And so that takes in the image that you're trying to do this thing on. And then the second input is your threshold value. So you can play around with this value as you need, but you're basically going to want to select a value that filters out what you don't want while keeping what you do want. And that's open to a lot of kind of fiddling and fine tuning. And then the third argument is the max val. So what that does is, depending on how you're doing the threshold, in our case, we're going to be doing what's called a binary threshold, in which if the pixel value is below the threshold we give, we want it converted all the way to black. It just shouldn't be there. And then if it's above, we want it converted all the way to white so that it stands out really high. And so that max val determines how white we want the things above the threshold to be. So a lot of times you'll just set it to 255 to have the max like whiteness and brightness you can have. There are some other kind of thresholding methods that you can look into in the documentation of OpenCV. For example, whether you want things to appear black in a white background or white in a background, you can choose that. But for the most part, a really common one you'll see is the one we're using, which is just the binary thresholding.
Okay, so back to our code. Once we established our overlap, and then now we're going to use we're going to have a new image, which is called our which is our threshold. And then we'll use the CV2 thresholding function. So our first parameter is the original. We'll use our overlap photo. Oops, overlap. And then this is where it's kind of open interpretation. You can use whatever values like. I'll just do 100 for now. Max value is 255. And then as Chase said, our type of thresholding we're going to do is this, it's a binary threshold. So we use the keyword thresh binary. And if you're wondering what this underline is, that's just how you ignore a variable in Python, because we're not going to focus on that variable, but this returns two variables. So we run this again. Oh, sorry, forgot to print it out. So now we're going to show this. We'll call this one thresholded, and then thresh. Now we run this. Now we notice instead of a bunch of random gray values, everything now is white or black. So either is what we want or isn't. And if we notice some of the extra noise has been thresholded out since we didn't care about that, and now we're focusing only on the cars part. And this is where there's a lot of fine tuning, and you can play around with the values you want. So let's say we want to threshold everything. We'll keep everything above 30. And we run this, if we notice it keeps too much. There's too much extra noise that we don't care about, and it just messes with our program. But we set too high of a threshold. Let's say we want to threshold, get rid of anything under 200. We'll see that, yeah, I got rid of all the extra noise, but it also completely got rid of our cars, our objects. So a lot of these libraries, it's up to you to fine tune however you want. You guys can play around a little bit, see what values you like. For now, I'll just leave mine at 100. And you guys can give it a couple tests for now, a couple of seconds.
I have a question for you, Tim.
Yeah, what's up?
Because you converted, so we had the original colored frame 1, frame 2, and then you converted it to gray before doing the absolute difference.
Yeah.
What does it do? What does absdiff do if it's colored still? Like if you used frame 1 and frame 2?
I believe it works. Like, we can try. We'll see what it prints. I believe it does work. However, one, it makes the math more complicated because we have to find the difference in 3 different layers. And 2, I think it ruins later on one of our functions we're using. I think the contouring does not work with colors. So we see, yeah, okay, the thresholding still works, or the overlapping still works for colored images. It's just for like simplicity's sake, we're going to be using grayscaled images. So grade 1, Texas still works.
Cool.
Yeah, okay, we're still good.
Well, we're kind of at a stop here. Are any of these functions confusing anybody? Do we have any
questions
so
you guys
far?
have? I don't know how to open chat.
I have chat open, so you can also unmute or type in chat if you want.
Do you guys?
We'll just take a couple seconds in case anybody has any questions.
Okay. I think we're good for now. You want to move on?
Yeah.
Okay. So next thing to look at is we look at our image. Yeah, we have the objects, but if you notice, every single car kind of has a giant black hole in the middle. And I think that would mess up our contouring. So we want a way to get rid of that. But luckily, once again, we can use math and OpenCV. And Chase can explain this one.
So to get rid of those holes in the middle of the car, and the reason we want to get rid of them, Tim kind of mentioned, but eventually our end goal is to draw a frame around that car and then put it back on the original image to show that this specific part of the image is moving, being motion tracking, right? So to draw the contours around, that's a built-in function in OpenCV, and it's really powerful. But with that said, if you have holes inside of whatever object you're trying to track, it's going to draw a contour there because it's technically like an outline, right? White versus black. And so we don't really want a bunch of like inner contours on our cars. So the way to do that is it's called dilation. And what this does is it basically fills in holes inside objects. And the way it does that is it basically weights the value of pixels, like it changes the value of pixels based on the pixels that surround it. So if it's inside an object, the pixels around it are going to be white pixels, so it'll fill it into white. It also has some side effects along the same thing in that it weights around pixels. So if you're right on the border, it's going to make the border more shaky because on the border of pixels, you're going to have neighboring pixels that are white and black, and it's not really going to know what to do. So dilation, it creates a little bit of fuzziness in the objects we're going to be tracking. But it prevents those inner contours, so it's generally a good idea, and especially if you can really fine-tune it to get some pretty good borders without ruining your shape too much, it'll look really nice. So the function in OpenCV, you're going to do cv2.dilate, and it takes in 3 arguments. So it takes in the image you're wanting to perform this function on, right? And then so the second argument is a thing called kernel. So what dilation actually is, it's actually a mathematical operation. It's like multiplying matrices, I believe. And so this kernel, depending on how you fill out that matrix, the kernel itself is a little matrix. It's going to be multiplying the bigger matrix of the image. Depending on the values you select for your kernel, it'll have different effects. So the one we're trying to use, we're trying to weight our neighbors, like the neighborhood pixels. And so our kernel is actually just going to be a solidly filled matrix with ones. And so whatever linear algebra behind the scenes is going on, it'll have the effect of basically our dilation and filling in those holes. And then there's also the third argument at the very end. It's just the iterations you want to do. So there's some fine tuning you can do with dilation. You can change your kernel to make things like more blobby or less bobbly is basically, and I'm sure Tim will go through it, but when you change the kernel, it will have an effect on that, as well as the amount of iterations you do of dilation will change the blobbiness. So basically, as you're dilating and closing in the objects you're trying to focus in on, it's just even more fine tuning to get it exactly how you want it.
Okay, so back to our code example. Just move this down a bit. So now we have our thresholded image with the blobs in the center. And this is the first time we actually use the NumPy library. And we're mainly just using it to create an array. So we'll have a kernel, and we'll use the numpy.ones function. All this does is just create a matrix or array of all ones. In this case, we want our size to be, I think for a kernel, it has to be any odd number. So for a test, we can do 7 by 7, and then the data type will be an unsigned numpy.unsigned integer 8. The reason why we use an unsigned integer with 8 bits is it's the same data type as the pixel values, which is 0 to 255, which is 256 bits, I believe. And that's the same thing as unsigned integer 8. And then now we're going to apply this kernel to our image. So we'll say dilated. This is a new image. Dilated equals cv2.dilate. We'll use our thresholded image. We'll apply a kernel. And iterations, we'll just do 1 for now. And so we go ahead and display this. So we notice now the holes are kind of filled in more as per the last for just threshold images. And once again, if you notice very carefully, there's like a small hole in one of them because it's not a perfect dilation. And once again, just like the thresholding, this is kind of up to your interpretation. You can fine tune how you want. For example, if I did a smaller matrix, let's say 3 by 3, sure, it fills in, but it's not a perfect dilation. You know, it leaves gaps, and that's still not good enough. And if I try too big of a number, let's say I did a 13 by 13 matrix to apply. If you notice, it's way too big, and it ends up just making a giant blob, and you can't tell what the original image is anymore. So, like thresholding, the dilation is kind of up to you. You can play around with it, make it how you would like it to be. And once we have that, let's set it back to something usable, such as we'll do 9. So now we've dilated our image, and now it's somewhat of a car shape now, and it's a solid image. So now what we can do is now we can apply the contouring, and this is where Chase can explain the hard math behind it, because I don't know it.
Yeah, so the hard math behind contours. So first of all, shout outs OpenCV library for having this find contours function, because it is very useful in motion tracking, facial recognition, basically anything you're going to want to do in computer vision, because you're looking at objects. You're going to want to actually outline those objects and detect them, right? So the OpenCV find contours, what it does, let's do the quick, like real low level mathematical explanation. Somehow, first of all, I want to say OpenCV is actually, the name of it is Open Computer Vision. That's where OpenCV comes from, which means it's open source. So if you actually want to look into the code on how this function is implemented, you can. But I am not as smart as anybody that would opt to do that. So I just read a wiki article on it. And what this function actually is doing is implementing some kind of mathematical theory that allows you to follow continuous edges in pictures, assuming that the edge has similar pixel values. So in our image we just made with dilation and everything, there's a pretty clear border between what we have in the white and then the background of the black. So it's really easy to follow that continuous border around for the find contours function, which is why we did all this pre-processing to get our images this way. And so now we have everything thresholded and filtered out and everything. We can just apply the find contours method, which takes in the image you're finding the contours on. Okay, I don't think I'm going to remember these. Okay, so there's 2 other arguments. One is the mode and one is the method. So the mode, I believe, is the algorithm that the find contours function actually employs to find stuff. And then the method is how much like you're trying to store of your contour. So basically, if you're trying to get a real detailed contour, it'll take more data to store the full shape inside the image, whereas you might be able to save some data by like eliminating some redundant points. So in our case, since we're just doing some image processing on one real like simple image and we don't need it to be super fast, we'll probably want just like the full accurate contour. But if you're doing like live motion tracking of a lot of objects, you might want more simple contours to make the processing speed faster. And then the mode, you can read up in the documentation of OpenCV. There's a couple different like methods that it follows the contour. And I'm not super positive on like which ones you would use where. In my experience in computer vision, I've pretty much only used like the default one they mention in the function representation, and I'm sure that's the one we're going to end up using here. But again, so just to find these contours, it's going to follow some continuous edges, which is why we did all this pre-processing before to finally get to this point.
Okay, so let's apply contours to our dilated image. and just move down a bit. So we're going to create a list of contours and a variable we don't care about. So underline, we'll use the cv2.findContours function. We'll check our dilated image. We'll be using, I believe this one's the mode, cv2.retrieve. Like, I'm not too sure what these do, but someone out there has defined the math for us. So all we got to do is just use the built-in keywords. cv2.chain prox. I think I kind of know how this one works. So instead of looking for all the points around a dilated image, it takes too much space to store every single point. So it does approximations. I believe it does like the corners. And from there, it can draw an approximation for you of what the dilation of the contours look like. So now we'll apply it. We have our final image. And we'll use the cv2.draw contours this time. What we're going to draw it on, we'll take our first frame. Let's draw on a copy of it for now. So it just copies the array of all the pixel values. And then we add our list of contours so it knows what to draw. The next number, it's which contour you want to draw, because it'll give you a list of all the contours. In our case, we'll just do -1, so it draws all of them. Next section is what color you want. And remember, in OpenCV, the coloring is backwards, so BGR 00255. Let's do a red line. And finally, the last parameter is just your line width. So I'll just make it 2, so it's visible. So finally, if we add this final image, we should be able to see, nope, sorry, hold on.
You need to capitalize contours and find contours.
Yeah, okay. So now it's drawn the contours around our previous shapes. Just open all these so it's visible. So you can see the steps we took. So we originally had our first 2 frames, which we couldn't tell much of what was going on. We ran it through an absolute differencer, so we figured out what pixels have moved currently between the 2 frames. We'll figure out what has happened. And then to get rid of extra noise, we'll be thresholding it, and that's how we cleared it to binary, black and white. Then we filled in everything with dilation to make all our objects nice whole objects to see. And then finally we added our contours. So, and this is the concept behind object tracking. And this is just an example of 2 images. But let's say we wanted to apply this to a video, so we don't have to manually run every single frame through a program. So if we just, I'll just close this for now. We'll just comp that out so it doesn't print anymore. So how we apply video, in CV2, there's a video capture. CV2 video capture. In this case, we'll do cars.mp4. You can feel free to use any video you have, just as long as it's in the same directory, or you give the absolute path. It will find it. And then we have while cap.is opened. This is the while loop that's going to play all the frames. We'll have our ret and our frame is equal to cap.read. So it's going to read the capture. Frame will be the current frame it's on. Return, this just returns true or false if there is a frame. So if there is a frame, it will have it im.show, CV2, sorry, CV2.imShow, our current frame, so colors. So that'll be our current frame. And then as we continue on, we add a break statement. This should be within if cv2.wait key. So either if it reaches the end and it waits 1 second, or we can have a custom break command. So ord in Python is just what's the ASCII value. So if it receives the ASCII value of Q, it'll know to break early. We just put break right here. Then we have else statement, else. Just this is just, oh sorry, this is out here. That's if there's no more frames when return returns false. And then at the very end, we want to release our capture and destroy Windows currently open. Let's see if this runs. Yeah, hold on, there's no wiki. This is lowercase, I believe. So once again, it's massive. It's kind of hard to see what's going on. So we'll just apply a scale again, just like last time. I'm going to reuse the scale, but you can feel free to use whatever scale you want. So we'll have a new scale, we'll call this one video scale, and it's going to be comprised of the old width, it's just times 2, and height times 2. So this is just twice the size of the images. So instead of a quarter size, it's half the size. And we apply the same scaling function, the resize function. So we have frame is now equal to frame CV2 dot resize. We're going to resize our frame, and we're going to use our video scale. Scale is equal to, that's a new tuple. So now we run this again. It should be in a much more manageable size that we can see everything. Okay, and from this point on, we've already established all the math and all the functions that we used previously, and we just reuse the same concepts from before. We'll find the overlap. So first thing we're gonna do is we're gonna grayscale this. So gray is equal to frame, CV2 dot convert to color. We'll use our current frame, and we use once again CV2 dot color BGR to gray. And then we have our overlap image is equal to CV2 dot absolute difference. And so now our issue is, what frames do we use? We want to be overlapping consecutive frames in a video. So we're going to do outside of out here, we'll just create a new array. We'll call this the previous frame. We'll use the numpy function again to create, this time, an array of all zeros this time. So it's just a black screen. Numpy zeros. The size would be the video scale, I believe. Video scale. And then the data type, once again, would be unsigned integer of, unsigned integer of 8 bits, like that. So that should be a black screen. Now we can use the absolute difference. We can difference our current frame, our grayscale frame, and the previous frame. We'll do that. And from there on out, we reuse the threshold once again. And you don't need to write this out. You can just copy it from before. I'm just going to write it out so we can, go through it one more time. Go CV2 dot threshold. Use our overlap image. We'll do 100 like before, 255 the maximum, and then CV2 dot thresh binary. And then after we threshold, what do we do after threshold? We dilate it, so we're going to have another kernel again. Equal to, actually, we can probably just reuse the old kernel up here, so I don't need to rewrite that. So we just apply our dilation. So dilated equals CV2 dot dilate. Our thresholded image, our old kernel iterations, again, will be equal to 1. And then finally, we'll find the contours and add them in. So CV2 dot find contours. A dilated image, CV2 dot rich tree, and then CV2 dot chain prox simple. And then after that, so now we can finally add the contours to our final image. CV2 dot prox. We'll draw it onto our original frame here after it's been resized. Yeah, frame, our list of contours, -1, and then we'll do 255 again, and line width 2. So if we were to run this command now, final. And at the very end, we got to make sure that we have to, our previous frame should now become the current frame. So, this way it cycles through. Let's see if this works. Oh, that's not good. Somewhere the size is not right. Okay, that's fine. Contours, drawing frame. Huh. Let me just check real fast. Scoot this down. All right, Chase, I need you to help me out because I'm blind.
Oh, dude.
This is not good. Let me just.
Wait, what was the error it's giving?
Errors for absolute difference. Oh, okay. So that means the grayscale size is not the same as the video scale size, which is strange. I don't know why that's happening. It should be the video scale. And then actually, I'll just edit this. See if this changes anything. Oh, it's height. That's why. Sorry, I always forget. CV2 may be width and height, but for most arrays, it's height first times 2, then the width times 2. Hopefully that fixes that. And so we run this again. Let's bring this back up. Run this again. Yeah, okay, so now we can play the video, and then every consecutive frame, it adds the contouring that we did. So this is pretty nifty. And to prove that this concept works on any type of video, as long as there's some sort of motion and a stable background. If we try our other video, race.movie, this is an example where the camera is much more stable, so the only thing you see is cars. So if you do notice, the contouring is not perfect, but that's always, you can fix that if you just kind of mess around with the settings and how you want the threshold to work, the dilation to work, how you want to draw the contours. And finally, what I think is the best example of how to use this and apply this is we look at the intersection footage. MP4. If you look at it, this tracks all people and cars. So this is pretty useful. And let's let that run. So yeah, anyway, so that is a really good example of how the object tracking works. It tracks every car. It even goes up to the point where I think you can track individual people if you check carefully enough. If you're like the thresholding picks it up. And from this point on, you can always customize this. You can have people in a different color, cars in a different color, cars in a certain direction, different color. And you can work with this to implement it in any program that you're working on. And finally, so where to next? So with this object tracking, you can use an autonomous driving. Let's say you want your car to track things it sees, like as it's falling down a pathway, and it can see where the pathway is moving based on the pixels. You can apply this into a counter or some sort of traffic manager, because it'll count like which cars are going which direction, and you can just have it like just gain data and process it somehow. And even machine learning, people use the OpenCV library for machine learning, and the fact that you can have it track an object and then have your network recognize what type of object, what to do from there. This is just like a base, and this goes with anything. But in general, with the OpenCV library, there's much more capabilities. There's a lot of facial recognition libraries that people I know like to mess around with. There's tons more image processing libraries that you can work around with. This is all free, but you can just find out what they have, look it up online. And there's even stuff like shape analysis and 3D. I believe there's some sort of 3D video reconstruction. And so these are just some things you can do with this vast library. But for us, I think we're good for this object tracking library.
We made an object tracking. I mean, it clearly all the code we wrote worked on that intersection, right? It's tracking everything.
Yeah, and it's up to you where you want to go from this point on. You can apply it to one of your projects, or just have this standalone because it looks cool to watch the cars. That's what I do. I just like watching the cars. If you have any questions, let us know. Feel free to unmute or ask in the chat if you like.
Yeah, so there's a question. I don't know if that's an I or an L. I think it's an I. Is it Ian? Because it's at the beginning of the name. Asked about good resources for learning. So at least in my experience for OpenCV and anything computer vision related, especially because they're so visually oriented and kind of applicable because of that in the real world, your best bet is kind of just start lamb. Dang it. Why? Oh, it's not capitalized. You fooled me. But your best bet is to kind of start with an idea of something you wanted. So say you wanted to track cars in an intersection with this, or I know in my project that I worked on in computer vision, I wanted to know the time left on my washing machine when I lived on campus so that I could go down and see if it was open or not. So kind of just start with an idea, and then there's a ton of resources online. OpenCV, it's obviously open source in the name. So everything is well documented and you can guide yourself. But there's also a ton of people online that just create resources of maybe you want to do this. Here's how to track a car, or here's how to recognize hand gestures or anything like that. So your best bet for finding resources is probably to start with the idea first and then look around about OpenCV implementations. There we go. I'm good at English. I just do math. But yeah, quick plug for IEEE quarterly projects. If you are interested in something like computer vision related, you can get a team together and work on it and apply it to quarterly projects. Or I know a ton of the annual project teams work with computer vision to like track driving, follow a ball or anything. So great resources within IEEE and tons out on the internet.
So yeah, this idea is just kind of like the base. It goes on from here. There's way more stuff you can do with this. Yeah, I think Grand Prix, Soccer Robot, they both, someone was advertising they needed more people for.
There's like Project Drive definitely uses computer vision because they're navigating a course. Grand Prix, same thing. RoboCup definitely as well because they're all like, you know, little robots trying to be people. So they need eyes.
They do need eyes, yeah. Yeah, as Chase said, the internet has pretty much everything you'll ever need. So I think you should work from an idea of what you want to do. And then there's bound to be someone who's either had the similar line of thought or had similar like problems. And you just kind of, there's plenty of stuff on the internet to read. And you can figure out which you want to go from there. But other than that, I think we're pretty much done. You guys can feel free to leave if you need. We'll probably just stick around for questions for a bit.
Technically, the event goes till 7:30, so I have nothing in my schedule until 7:30.
30 minutes of questions. But actually, we advertised for 7 only, I think, on the Facebook. Yeah, I don't know where the 30 came from.
7:30 on the Facebook. I have it open right now.
That's not good.
6 p.m. to 7:30 p.m. Oh, and then in the text below, it says 6 to 7 p.m. We're a little bit confused around here.
Yeah. Other than that. But cool. Thank you guys for coming and listening along. This is pretty much it, right? Yeah, that's where. You want to stop recording, Chase?
Oh,
I think it's still going. But other than that, I think we're good.